I'm happy to welcome our next speaker, and Marcin Jastrzębski will come back to interferometry and sensing. So I'm glad we are having this diverse session. Please, Marcin, the stage is yours.
Okay, thank you so much for the introduction. And I actually wanted to start with this. Oh, oops, something is not responding here. Why can't I? Oh, okay, sorry for that. So I wanted to start with this picture, with this picture of this box. Maybe some of you don't know what is it, and it is a laser that I've been working with for a few months now. And it's a special laser because, well, most of you have probably seen lasers, and this one is a little bit different because it doesn't generate any, it doesn't have a constant power. It generates really fast pulses of light. So that's going to be the topic of my presentation. I want to present to you the work that we've been doing in Center for Quantum Optical Technologies in Warsaw with my colleagues. My name is Marcin Jastrzębski, and I'm a bachelor student from Poland. So let's just start with those impulses. These are called femtosecond impulses because they are, really fast, and the duration of such pulses are like few femtoseconds, or maybe 50, something like that. And those impulses are used, for example, in chemistry or biology. I'm not a specialist in that thing, but for example, if you have very fast pulses, you can observe chemical reactions in slow motion, for example. So it's used there, and those impulses have some properties. For example, as you can see, they are very narrow in time, but since we can't have the time and energy determined at the same time because of uncertainty principle, they have a very broad spectrum. And we wanted to measure them. There are some methods with measuring femtosecond impulses. It's not a trivial task, and here is our idea. So as you can see, we have a pulse here, and we split it into two separate copies, and one of them is being shifted in time relative to the other, and the other one is shifted in frequency. You can see that this one is blue, so it has a little bit different wavelength. And then we measure the interference of those impulses, and we measure the visibility of the impulse. Of the interference, sorry, the visibility of the interference. So we basically take those two copies and say, if they are a little bit different, like in time or in frequency, do they want to interfere or not? So let me show you the idea. So you have like two pulses that are the same, and if you shift one of them a little bit in time, they don't overlap completely. They overlap a little bit less. And then you also shift the other one in frequency, they also stop overlapping. So that's the idea that stands behind this method. And you can see that in this setup, there are no nonlinear effects. So what are nonlinear effects? For example, generating a second harmonic or something like that. And such processes tend to be very inefficient energetically. You have to, pump the crystal, put a lot of power there, and you obtain a very weak beam. So this method is suitable for single photon measure, which is something I would say something great. And to show you how do we achieve those delays. So the time delay is pretty simple. You have in the lab, you have some some optical elements, some fibers, as you can see, and there is a collimator on a moving table. So by changing the position of this table, we can control the time delay of one of the impulses. And in the other arm, we perform frequency shift, and this is a little bit less trivial because we use this box, I would say. It's an electro-optical phase modulator. And how this works. So here you can see there is an input, you know, it's a fiber and the impulse comes here. There's of course the output and the impulse comes out. And there is this cable with RF, and RF stands for radio frequency. And it's in our case 15 gigahertz or something like that. These are the ranges that we operate at. And inside this box, you have a crystal that is called lithium niobate, as I recall. And this crystal has a property that when we apply voltage to it, its refractive index changes. So by applying voltage to this crystal, of course, not a constant voltage, because that would be just the phase shift, but like linearly in time changing voltage, we are able to shift the pulse in frequency. And also, like, where do we get this radio frequency signal from? So before splitting the impulse to two copies, well, you remember with those shifting in time and frequency, we also like split it once again, or like the first time, and we trigger the photodiode, and then we amplify the signal with an amplifier. There is also a generator, because photodiode is serving us only as a clock, because, you know, those are just impulses. We have to make sure that when the impulse hits this crystal, there is voltage applied with proper phase. So we have to make sure that, you know, the length of cables and fibers in this RF loop, as I call it, is appropriate. And there is also an element that is a mixer, and it's going to be important later. It's an element where we apply some voltage, and we can change the amplitude of the signal. So you may say, okay, so you shift impulses in time and in frequency. You have some modulator to shift in frequency. How much shift do we have from this modulator? Because as you recall, those impulses are very broad in spectrum. I didn't say that, but it's something like 12 nanometers in our case. So it's really, really broad. And if you want to shift those pulses in frequency and observe the interference, you probably want to shift as much as those 12 nanometers. So it turns out the formula for this frequency shift is here. So here is the frequency of this radio frequency signal. So in our case, it's like 15 gigahertz. Voltage peak to peak is connected to the power of this signal. And there is also this pi, which is just a constant of this modulator. You know, it depends on this crystal, of its diameter and such. In our case, it's like 5 volts or something. So applying all of this, how much shift do we have? And the answer is 0.2 nanometer. So as you can see, we have 12 nanometer spectrum, and we can shift only 0.2 nanometer. Well, we have to do something with that. And of course, some of you may know that there are optical elements such as spectral filters, but which are essentially filters that you can put into the optical system, and the spectrum of the laser gets narrower, of course. But we actually didn't have like such narrow filters, because, you know, it's 0.2, but we probably would like to measure something like 0.05 or something like that. So we decided to build a 4F spectral filter, and let me just quickly tell you what it means. So here is the scheme, and the idea is that we basically use a diffraction grating, and as you probably know, diffraction grating works such that that it reflects light, but different wavelengths refract at different angles. So we essentially split the beam into its spectral components, and then we use a precise, slit. It's just a slit with a screw, so we can regulate the how narrow it is. And then there is a second diffraction grating to kind of combine those remaining spectral components together. And the 4F name comes from this, that here we have a lens, and the distance from this grating to the lens is its focal length, and again to the slit is also focal length. From slit to lens, again focal length, and from lens to the grating, it should be also the focal length. And using that, we can actually perform measurements on various spectrums and be able to achieve shifts as big as the laser spectrum now. And here is the other thing I said about those, we can narrow the laser spectrum, we can measure the shift, but how to actually measure that? And the answer is you use a spectrometer. Spectrometer is a simple, depends of course, but it's a device that you have a diffraction grating, and again you put the beam on the diffraction grating, and it is reflected on various angles, depends on the wavelength, and then you use some kind of detector. But the problem is, because you of course can buy some spectrometers online, you can buy these, and it's not a problem. However, sorry, let me just I don't know how to. Okay, so here is the laser and detector. Actually, those commercial spectrometers have very broad wavelength range, and they are not precise enough to observe those shifts, to measure those narrow wavelengths. So we decided to build our own spectrometer, and it may seem confusing at first, but here is the laser. Here we use the second order diffraction, and then we reflect it back on the diffraction grating and use its second order diffraction. So we essentially use the fourth order diffraction for this, and then we have a detector, and we calibrate the spectrometer. And by using this fourth order and using such an angle on this diffraction grating, we are able to achieve such a high resolution, which means we can distinguish between those like shifted impulses. We can actually see when we shift the pulse in frequency by like 0.2 nanometer or something like that. We would be able to distinguish such change with a commercial spectrometer. Oops, why can't I? Oh, so spectrometer is used to measure the frequency shifts. And basically, we use it for a setup to change the spectral widths to observe how it looks, and also we use it to calibrate the frequency shifts we get from the modulator. Because our measurement looks like this: we have this mixer that I mentioned. It's a small element here, but it's really important, and we change the voltage on it. And then we use the spectrometer to calibrate what frequency shift do we get according to this voltage on the mixer. So you may say, why don't you just observe it like in lifetime, live? But the thing is that if we want to perform single photon measurements, we can't use like any spectrometers. because we don't have any, and it's pretty difficult, as I recall, to build a spectrometer for 800 nanometers for single photons. It's much easier to build a regular. So by getting this curve, we can use it to later translate voltage into frequency shifts when we are performing our measurements. Sorry. So yeah, now you may say, okay, you shift one impulse in frequency, the other in time. What is the quantity that you measure? And we use single photon detectors. And the quantity we measure is called G2, or second degree coherence function. So we basically measure the coincidences on the detectors divided by the values of photons on each detectors. So we basically have two detectors, and we ask how many photons are getting to one of those detectors, to the other, and what are the coincidences. So how many photons we have that, you know, achieved detectors simultaneously. And then G2, or this second degree coherence function, is connected to such a quantity called short time Fourier transform. And that is the connection, basically. So you have 1 minus half times the visibility. It is the visibility of the interferometer. So you know, we used Hongu-Mandel interferometer that is based on Hongu-Mandel effect, and you know, it's if the interferometer is well built, let's say correctly, the visibility is like 0. It's like 95% or something like that. And there is also this short time Fourier transform, and maybe to make it more clear what this short time Fourier transform actually looks like. So this is the equation for this. So here you just have an impulse. The epsilon is the amplitude of the electric field. So you can see one of them is shifted in time, the other is not, and you also have this impulse shifted in frequency. Where mu is this frequency shift from the modulator, and the tau is the time shift that is applied also here. So here I wanted to also show you the results, because you say, okay, you have this setup, 4F setup, spectrometers, you shift one impulse in time, the other in frequency. You showed us some kind of coherence function, short time Fourier transform. What do you actually get, and what is the, does it make sense? So we simply we make a two-dimensional map of this short time Fourier transform with respect to time shifts and frequency shifts. So let me just show you how they look. This is how they look. Oh, sorry. So the bottom pictures are the experimental results, and we used different FWHM is full width at half maximum. That's something that I didn't mention earlier, but it's basically the spectral width of the pulse. So we just used our spectral filter to have different spectral widths, and then we perform the measurements, and the bottom pictures are the simulation. And as you can see, it matches pretty well. And you may say, what are those four legs, or that's how we call it. So it turns out that if those beams were Gaussian, as I showed on the very beginning of my presentation here, if this was Gaussian beam, then we wouldn't see such artifacts here. But it turns out that when we use our precise slit in the 4F setup, then when we cut some of the wavelengths, the resolution is pretty good there. So we have more of something like a rectangle, not a Gaussian distribution. So that's why we have those 4, and you may see in simulation there is also 4 of these. So what can we like take from that, from those pictures? Oh, we can see those spectral widths of the pulse and temporal widths of the pulse, because you may see when the pulses stop interfere at what shifts, and at what time shifts and frequency shifts. We also made some measurements with measuring the chirp, which will look like the pulse would be rotated a little bit, but we had actually a reliable way of changing this chirp with moving the diffraction grating, one of the diffraction gratings in the 4F setup. But as some of you may know, when you work in lab, something works and then something gets disturbed by accident, and then it doesn't work. We also experimented with rubidium atoms because they absorb light at 795 nanometers or something like that, and they introduce a lot of interesting phase into the setup, and depending on the temperature. So let me just quickly summarize what I said. So it is a new method for measuring light pulses. The whole measurement is controlled electronically. We control the stepper motor with the time shifts and the voltage on the electro-optical modulator for frequency shifts. And then we collect data from single photon detectors, or we could also use photodiodes or avalanche photodiodes for single photons also. And the huge advantage is that we get both spectral and temporal width of impulses, and there are no nonlinear effects necessary, which makes it this method suitable for single photon measurement. Thank you very much.
Many thanks, Marcin, for the presentation. This is inspiring. I was trying to put into my mind, how did you manage to do all this in the bachelor thesis? But this is probably the question I should not ask at the conference. So let us see whether there are more interesting questions regarding to your work in the chat. For the moment, I recall a lot of announcements that we are going to have a picture actually at the end of this session. So stay tuned, everybody, if you want to be on a picture. And now there is a question that, okay, still the one that I posed. And I am curious how this new method that you have developed is different from existing methods, because I'm not from the field, so I'm very curious, what have you offered?
So basically, there are known methods, for example, using a Fourier spectrometer. So it's just with the time shifts, but you only get one dimension from it. So the advantage is that we don't get only the only the temporal width, but we get both, which is huge. And also, of course, there are methods that can show us both dimensions, but then we need to use nonlinear effects. And if that's the case, then we can't perform single photon measurements. And that's the advantage, that we can have very weak impulses of light and then perform the measurement. Because if you have nonlinear effects, you have to pump the crystal, put all of the power of this laser to it, and you can't use single photon detectors. So I would say that's the advantages.
Okay, thanks a lot. So it's something that cannot be compared with any other because it just didn't exist. So it's a unique thing that you're proposing. That's fantastic, and I'm waiting for questions from the audience, which I think will come soon. in the meantime, I permit myself to make another question. So, oh no, let me read the question from the audience. So the question is from Ioannis, and he's asking, have you done any correlated photon experiments?
Okay, so I suppose you mean that we would generate like photons from some nonlinear crystal and maybe then try to use them. We are working on it, but we didn't manage to complete that yet. We are working. We want to use Sagnac interferometer, but it's still work in progress.
Okay. The next question is coming right away from Nasser, and he's asking, can you differentiate between single and multiple photon measurement with your detector?
So I would like to ask, what is the difference between single and multiple photon measurements? Because I think I don't know what that means. If you could elaborate on that.
Let's see what Nasser will write. In the meantime, I would have interpreted as if your photon detectors are photon number resolving. So you can distinguish between the fact that you measure just one photon or two photons or three photons or four photons, if these measurements have a distinction between themselves in your detector.
Well, I don't consider myself a specialist of photon detectors, but our detectors work like this, that we have like a superconducting nanowire, and if there is a photon there, it will increase the temperature of this wire and break it out of superconductiveness, and we just simply set a time window of integrating, and then we get the number of how many photons we got during this time window. So for example, we just set like the time window to let's say 100 milliseconds, and then we get the number of photons. But yes, if there was like one photon, we could distinguish that but of course there is also some noise. So I would say if we saw one photon on the detector, it wouldn't actually mean anything, because we have some noise always, and we have to like average everything. So I would say if there was just one photon, we wouldn't like detect that, I think.
I see. So when there is more specification coming, so the Nasser specifies if it's a single photon at a time or the two photons at the same time. So in a sense, if it's a two photon state, would you be able to notice that there are two? But how you explain the detector work, I imagine that it will react similar to whether it's just one photon or two photons at the same time. Am I correct?
No, I think it would detect two photons, because like it's only about the energy that we get from this. So I think it would be distinguished as two photons.
So you see the size of the response. So you see whether it responded a little or more.
Yeah.
I hope Nasser is satisfied with the question, with the answer. And let's see if he will write more. In the meantime, maybe I push through the question I had. No, I have not other questions at the moment. Oh yeah, I am very curious also what let's say there is this lots of interest in the pulsed light generation, especially when you have one photon in this broad in the broad pulse, because then there is this way of having let's say entanglement between various harmonics, various frequency harmonics of the pulse, and so have some interesting quantum state of light practically generated from with this device. So I imagine that you're looking at this as well, right? Because this the answer from your the previous questions was that you were trying to generate some quantum light with it.
Yes. With the quantum light, we were trying to generate it. but we, oh, sorry, I'm just switching between those, but we didn't manage to calibrate this yet. So we were just performing our measurements of on coherent states. So it basically means that we like took the pulses from the laser and we inserted some, it's called ND filters, the filters that lower the power so that our detectors wouldn't burn, you know, and with the entangled photons, we don't have any results yet.
All right. Many thanks, Marcin, and Nasser was extremely satisfied with your answer. And I would like to invite you to remove your screen, so we will have you in the full screen, and to greet the audience in your native language.
Okay. Pozdrawiam wszystkich. Dziękuję bardzo za możliwość wzięcia udziału w tym wydarzeniu. Mam nadzieję, że jeszcze kiedyś się spotkamy. Pozdrawiam. Thank you.
Thank you so much.